All right, welcome to lecture 2.2, focused on sp2 hybridization. As we discussed last lecture, hybridization is a way that we understand the atomic orbitals of the s and p orbitals and the way that they combine to make the structures that we know and interact with on a daily basis. So the sp2 orbital is going to be, for now, we're going to focus on this as the alkene situation when we're dealing with double bonds. Now, you may be familiar with the idea that a double bond is composed of two different bonds. A sigma bond, which we discussed last lecture, represents a bond made by a hybridized orbital, and a pi bond. And we're going to figure out what that pi bond really is today and what it looks like when we draw the orbitals. So to get started, let's understand that the alkene, now we only want to connect to three different orbitals. So if we look at this carbon here, we're going to see that there are three different, there's a hydrogen, and another carbon, let's say. So here, the carbon is only going to want to make three hybridized bonds. And to do that, we're going to mix three of our orbitals. Now, the new orbitals that come out, we're going to see that if we kind of imagine this mixing pot, one of the three orbitals is S, which gives us a 33% S character. And two of those orbitals, the remaining two, are P, which gives us a 66% P character. Drawing the new hybridized orbitals, what we're going to see is something like this. In between the S and P energy levels, we're going to have our new three, right? Three orbitals went in, three have to come out, and these are now going to be our two sp2 orbitals. Right? To be clear, this 2 represents the energy level, and the lowercase 2 represents the hybrid, since we have two p's mixed in. Now, what's interesting is that we've left this other 2p orbital alone, and it's going to be higher in energy accordingly. When we fill in our electrons here, what we're going to see is that we have three hybridized orbitals that are capable of making sigma bonds. But then we have this weird orbital up here, and we're going to call this the unhybridized p orbital. All right. Now, importantly, when we have three things around a carbon like this, which again I will touch much more specifically on in lecture 2.4, we're going to have the sp2 hybridization, which is the shape trigonal planar. That looks something like this, where we have three things connected, and they're all flat. There's no three-dimensional structure whatsoever. The bond angles here are 120 degrees for the sp2 hybrid. But let's break down what this looks like from an orbital drawing perspective. And we'll do that using ethene, a simple molecule here. Focusing on the red carbon, we see that that red carbon is connected to two hydrogens and connected to the carbon via a double bond. So let's draw the hybridized orbitals in black here. And these are our sp2 orbitals. Now, we can imagine that these hydrogens, again, bring in their 1s electron and are capable of making bonds. So these two orbitals down here represent the two bonds there to the hydrogen. And we can represent these bonds as carbon 2sp2 orbitals making bonds to hydrogen's 1s orbital. Again, we draw this as a straight line, typically. Now, the remaining sigma bond is going to come from the other carbon. It itself is also an sp2 carbon, so it's going to provide its own. And together, we're going to have our last sigma bond there. So these are the three sigma bonds represented, if I want to color code them, by this bond, and one of the bonds of the double bond. But what's up with this remaining bond? Well, this is where the unhybridized p orbital comes in. By itself, this unhybridized p orbital would look something like this. a big dumbbell connected to the carbon, containing one electron. And that doesn't look very stable, but the important consideration here is that the other carbon is also going to have a similar unhybridized p orbital. When it comes to double bonds, it's going to take two to tango. So now that we have these two orbitals, these are actually capable of interacting with each other. And this is what we understand as the pi bond. Now, sometimes you might see this represented differently. One way you might see a pi bond represented, if we imagine the sigma bond here, is drawn like this, above and below the carbon. I prefer to draw it this way to maintain that p orbital structure. Now, just to finish up this last diagram, we can imagine that this now represents the pi bond, the interaction of two unhybridized p orbitals. Two unhybridized p orbitals interacting. This carbon, of course, has its own sp2 orbitals interacting with the hydrogen, which would fully represent the orbital diagram of ethene. Hopefully now we have a better understanding about what makes a sigma bond between hybridized orbitals different from a pi bond between unhybridized orbitals. One last important consideration to look at is that a sigma bond by itself, if I look at this one for example, is able to rotate. These carbons are able to rotate no problem. However, the pi bond requires that these p orbitals are in the same plane. They need to be in the same area, above and below the carbons, for example. So if I was to rotate this carbon and push it into the page, let's say, that would actually break the pi bond. And as such, an important rule about pi bonds is that they cannot rotate. And this is a very fundamental thing that's going to crop its head in many different units going forward. It's going to lead to some problems and some good things as well. But in general, it's good to know that these pi bonds are unable to rotate for that reason. Now, all we have left is to do the sp hybridization in the next lecture. I'll see you there.